Hello guys, once again welcome to my YouTube channel. In my previous presentations we always talk about these balance Y delta configurations. Now this time I'm going to share to you and discuss with you the asymmetrical Y and delta configuration explanations. Let's brainstorm this unbalanced load. Okay, the questioner is what gives rise to a three-phase system to become asymmetrical or unbalanced? The unbalance happens, it's either on a source or the load configurations. Say for example, let's take a look at this. For a Y balance, unbalanced connected load, let's example, the line voltages, this is the line voltages here, the VAB, VBC and VAC, these are the line voltages, or the VAN, the phase voltages here is VAN, BBN and the BCN. Okay, these are not symmetrical from each other, meaning they don't have the same values, so that's why they call it asymmetrical. And also the impedances are also asymmetrical. They don't have the same values with as compared to the balanced load. They have different values, and at the same time the displacement of the phase angle for this one is not equal. The displacement of 120 degrees, they are not equal from each other, and they are apart, or they don't have this 120% equally apart from each other. The phase angle here, the displacement, and also the current magnitudes of the IB, this one, if you're going to solve this IB here, the IC, IB, IA and the IC, they are not the same in magnitudes, unlike with that of the balanced load. And most of all, the current in the neutral is not a zero. It is, there is a current that is being developed that will pass through the neutral and go back to the source. So if this is a zero line, line neutral zero, the I line neutral here is the IA here is equals to the IA plus IB plus IC equals to 0. So that is basically by the Kirchhoff's current law. Okay, let's have some exercises. Calculations procedures. Given the balanced voltage source, okay, our source is probably the let's do it the Y, balance of Y. So we have a 220 degree phase angle, then negative 120 degrees phase angle plus 120 degrees phase angle, or negative 240 phase angle for this C. Now for the Y load impedance, they are not also the same in the values. We have here the ZYA here. This is a 25 ohms, so this is a pure resistor load, okay. And we also have the ZYB here, okay, the ZYB here, this is a capacitive load, and this ZY 10 plus J8 imaginary 8 is inductive load. So basically that is the unbalanced setting of this Y configuration load. So if you are going to compute for the IA, they differ from each other, from the IB and the IC. So this is the formula for the IA, for the IB, the VAN here, this is the VAN here, then the ZY for this impedance and this phase Y phase, and also the same thing with the IB, VAN divided by ZY B and the BCN. Okay, and the neutral line here, you have the formula here is I neutral is equals to negative IA plus IB plus IC. That is neutral. It has to have a neutral. We're going past to the neutral line, and we'll go back to the source. Okay, let's substitute those values from the line current IA, which is VAN. So CYA. So we have this 220 degrees divided by the resistor, and you get all these complex numbers and the magnitude to phase angle. You have it here, and same thing with the IA and IB. You have this, and you have all these things. You can just compute. These are correct. Okay, so if you can see here, you can see the magnitude of this 8.8, 7.2, 7.4, 17.4. I'm sorry. You can see that they don't have the same magnitudes, because this is an unbalanced or asymmetrical phase configuration, load configuration, I mean. So if you're going to get the line current, you need to convert this magnitude phase angle to the complex number polar. This one, and this one, the three of these. Then you can compute that. Then you can get this the polar and the phase complex number and the phase magnitude and the phase angle of the line neutral, which is 20.9, 14 degrees. Now let's go to exercise delta, the delta unbalanced load here, and you can see this unbalanced loads. The source is a delta balance load. Okay, the delta, sorry, the balance source delta. So we have the line to line voltage. We can have this is the line to line voltage, the BAB here, the line voltage BBC here, BC, and the line voltage CA here. Okay, so the ZAB is given the phase, the impedance of the delta load phases, which is ZAB. Okay, you have it there. It's 20. It's a capacitive load, and the CBC it's a pure resistive load, and the ZA is inductive load. These are the values. We are to find for the delta load phase current. So we are to find for this phase current here, the IAB, the IBC, the ICA, and we also ask to find for the line current IA, IBC, IB, and IC via the Kirchhoff's current law. Okay, you have it there. And so if we are going to analyze the Kirchhoff's law for the IA, IB, and the IC, you have this IA, okay, this one, plus the ICA minus the IAB. Then when we transpose this to the right side, we have to remain this IA. This becomes IA is equals to IAB minus ICA, and the same thing with the IBC is equals to IBC minus IAB, this one, and also the IC is equals to ICA minus the IBC here. So let's try to substitute this in this manner, calculation procedure. Say we have this IAB, you see this IAB, you have the polar equation here, this one, this is the polar equation, and this is the magnitude and the phase angle here for the IAB, and the IBC, this is also the magnitude to phase angle, and you have this polar equations. The same thing with the ICA, I'm sorry, and you have all these for magnitude, the phase angle, and this is the polar equations. So if we add them all, you will see that these magnitudes here are not the same. The IA, the IB, and the IC, they are not the same when you add them all. Okay, that's all, folks. You may choose to subscribe and share, and have a good day and stay safe always. Thank you. Bye bye.